Hello everyone. So in this video of thermodynamics chapter I'll be talking about second law of thermodynamics, Gibbs energy, then Gibbs function and equilibrium constant. Second law of thermodynamics. Second law of thermodynamics states that the total entropy of a system and its surrounding increases in spontaneous process. Means delta S total is equal to delta S of system plus delta S of surroundings is always be greater than 0 if the process is spontaneous. Let's understand with example. For example, hydrogen gas is combining with oxygen gas to give you hydrogen oxide or water molecule which is in liquid state. Here delta S, that means of system entropy, is given minus 327 joule per Kelvin. Enthalpy of the reaction is minus 572 kilojoule at 298 Kelvin. To find delta S total, we need to know the surroundings delta S value, and delta H for reaction is given minus 572 kilojoule when 2 moles of hydrogen and 1 mole of oxygen is combining to give you 2 moles of liquid water. 527 kilojoule of heat is released, which is received by the surroundings at constant pressure and 298 Kelvin temperature. So the entropy change in surroundings would be delta S surrounding will be Q reversible process upon T is equal to 572 multiplied by 10 raised to 3 joule upon 298. We will be getting delta S surroundings value 1919 joule per Kelvin. Now delta S total will be delta S of system plus delta S of surrounding. Delta of S of system is given minus 327 plus delta S of surrounding we have calculated 1919 kilojoule per Kelvin. So we are getting value 1592 joule per Kelvin, which is greater than 0. So delta S total is greater than 0. So the reaction is spontaneous. So it follows that to decide spontaneity of a reaction, we need to consider the entropy of system and its surroundings. If delta S total is greater than 0, process is spontaneous. If delta S total is less than 0, process is non-spontaneous. If delta S is equal to 0, the process is at equilibrium. Now, Gibbs energy. It was very much necessary to determine delta S of system and surrounding for predicting the spontaneity of a reaction. We are more interested in the system, or you can say the reaction mixture. It is convenient to consider the criteria of spontaneity in terms of thermodynamic property of a system, and that property was solved by a scientist named as J.W. Gibbs, who was American. He introduced one term which is called as Gibbs energy. It is thermodynamic property denoted by capital G. The Gibbs energy is defined as G is equal to H minus Ts. G is Gibbs energy, H is enthalpy, T is temperature in Kelvin, and S is entropy. Here H, T and S, all three are state functions. That is why Gibbs energy is also a state function. The change in Gibbs energy at constant temperature and constant pressure will be given by delta G is equal to delta H minus T delta S. Now, Gibbs energy and spontaneity. The total entropy change that accompanies the process is given by, we have just learned in second law of thermodynamics, is delta S total equals to delta S of system plus delta S of surroundings. Now we are dropping the subscript cis and we are stating delta S plus delta S of surrounding. Now what is the relationship between delta G and delta S total? According to second law of thermodynamics, if the process is spontaneous, so the delta S total value would be greater than 0. If delta H is the enthalpy change accompanying a reaction, the enthalpy change of the surroundings would be minus delta H. Right? So surroundings delta S value would be minus delta H upon T. Now the value of delta S of surrounding I am substituting in the first formula, that is delta S total equals to delta S plus delta S surrounding. Here I would be getting T delta S total equals to H minus T delta S, and I know that delta H minus T delta S is equal to delta G. So delta G is equal to minus T delta S. So for spontaneous reaction, S total is greater than 0 and delta G should be less than 0 at constant temperature and pressure. The Gibbs energy of the system decreases in spontaneous processes. Second law leads to the condition of spontaneity, which is summarized like delta S total if greater than 0 and delta G is less than 0, the process is spontaneous. If the delta S total is less than 0 and delta G is greater than 0, the process is non-spontaneous. And if the delta S total value is equal to 0 and delta G is also 0, the process is in equilibrium. Now spontaneity and delta H or delta S. From the formula, delta G is equal to delta H minus T delta S, where the temperature and pressure is constant. The temperature term determines relative contributors of delta H and delta S to delta G. Delta H and delta S are both negative, then delta G will be negative. Only when delta G is more negative than T delta S. It is only possible at low temperature. Delta H and delta S both are positive, then delta G will be negative. Only delta S is greater than delta H. It is only possible at high temperature. For delta H negative and delta S positive, it follows delta G is negative regardless of any temperature. For delta H positive and delta S is negative, then delta G is positive regardless of temperature. Such reactions are non-spontaneous at any temperature. Now, temperature of equilibrium. We know formula now, delta G is equal to delta H minus T delta S. It will also give us T is equal to delta H upon delta S. T is the temperature at which the changeover from spontaneous to non-spontaneous behavior occurs. If delta H and S assumed to be independent of temperature, introducing of temperature dependence of delta H or S would not cause significant error to moderate temperature range. Now the last is Gibbs function and equilibrium constant. Gibbs energy change for a chemical reaction was given by, the equation was given, and the equation is delta G is equal to delta G naught plus RT ln Q. Here delta G naught is standard Gibbs energy change when the reactant and product in a reaction are in their standard states. Q is reaction quotient, is analogous to that of equilibrium constant. Now if we are considering this reaction and all reactant products are in gaseous state, and delta G is the equation written for the reaction, and here I am writing Q as reaction quotient as concentration of C raised to power C, concentration of D raised to power D upon concentration of A raised to power A, and concentration of B raised to power B. And If I writing in terms of partial pressure, then partial pressure of C raised to power C multiplied by partial pressure of D raised to power D upon partial pressure of A raised to power partial pressure of A raised to power A multiplied by partial pressure of B raised to power B. And now I am saying here delta G is equals to 0. So the equation would be 0 is equal to delta G naught plus RT ln Kc. Right, I have replaced C concentration multiplied by D concentration upon A concentration and B concentration by Kc, and partial pressure of C multiplied by partial pressure of D upon partial pressure of A multiplied by partial pressure of B I replaced by Kp. So I can say here delta G naught is equal to minus RT ln plus Kc, or and delta G naught is also equals to minus RT ln Kp, or delta G naught is equal to minus 2.303 RT log base 10 Kc, or delta G naught is equal to minus 2.303 RT log base 10 Kp. So this is the relation between the Gibbs function and equilibrium constant. Thank you.